Question 17. A student sets up the circuit, like in this figure, to investigate the resistance of a lamp. Cool. 17AI. The student also needs to add a voltmeter to the circuit. On figure 17.1, draw where the voltmeter should be connected. Just a reminder, this is what a voltmeter looks like, and it needs to be in parallel with whatever we're concerned with. Now, the question says they're investigating the resistance of a lamp. So we're going to have to know the voltage of the lamp and the current of the lamp in order to find out the resistance using Ohm's law, V equals IR. This is our lamp, so our voltmeter needs to be looking across either side of this lamp. For extra kudos, use a ruler to do these lines here, but they won't penalise you so long as your drawing isn't too messy. Question 17A, part 2. The student takes readings of potential difference and current and records them in this table. There are 2 mistakes in the results table. Write down 2 mistakes and suggest how they should be corrected. Let's have a look at this table here. Potential difference in volts, fine. We've got some numbers, great. Current, ooh, well they've not said what their current's measured in, so that's probably something that's missing. No unit for current. Okay, how would we fix this? Well, I guess the only way to fix it would be to put a unit there. So put unit for current in table. Probably going to be amps, might be milliamps, but remember to give a suggestion for the unit. So you could put A for amps or amps there, either's fine. As for mistake number 2, let's have a quick look back in here. Those numbers seem all fine. Looking at these numbers, this first one seems to be a bit of an odd one out because it has all these decimal places. Feel sorry for the ones below it. They've been recorded to a lesser precision, but either way, we've not been consistent with our recording of data. So mistake number 2, current 1 not recorded to same precision as others. And to correct this, we need to record current to 1 decimal place. That seems to be what they're doing there. Or actually, you could argue that they've all been given to 2 significant figures. Question 17A, part 3. Calculate the resistance of the lamp when the potential difference is 4.0 volts in table 17.1. Let's make sure we've got that table somewhere handy here. So 4 volts here, and our current was 3.2. That's going to be useful, so let's write this down. Voltage is 4 volts, current 4.0 volts. Let's be consistent here. And the current was 3.2 volts, and they've given us an equation to use. So potential difference equals current times resistance. Looks like Ohm's law. Here you can substitute your numbers in straight away, then rearrange for our unknown, which is resistance. I like to do it the other way just to practice my algebra. I'll rearrange first. So we want the resistance. This implies that our resistance equals voltage divided by current. Now I'll sub in these numbers that I've got here. Voltage is 4.0 divided by current 3.2. Just to make it easy for my brain, take out the calculator again. So 4 divided by 3.2. I could put 4.0, but I won't bother. 5 over 2, 1.25. That'll do. Some of you might be worried that I'm giving this to a greater precision than the numbers that have gone in. You're right. I can also get away with putting 1.3 ohms because I'm rounding it to 1 decimal place, or 2 significant figures. This answer will be accepted, but at GCSE, having 3 significant figures is also accepted. They'll accept this answer too. Question 17. BI. Plot the missing point at 1 volt on the graph and draw a line of best fit. Okay, so let's get that data out again. Potential difference 1 volt, current is 1.0, so that needs to go somewhere on here. Got to catch myself. I don't want to ruin this graph with pen marks. I only get 1 chance really, so I'll put this to one side, get my pencil out. That way I can rub it out if I need to. So 1.0 potential difference, there we go. 1 amp of current, and I'll make a little cross here. So that's my first part of the question done. Get our ruler out for the line of best fit. Put that down there. Interesting. So as I line up my ruler, I can see that my data doesn't follow a straight line trend, but that's okay. Some of you might have already figured out that this kind of curve is quite common for an electrical component. You see, as a current increases in a component and causes it to heat up, the resistance would increase, therefore making it hard to get more current. So it looks a little bit like the kind of curve you'd get for a filament lamp. So a bit like this. In that case, let's go with our gut instinct and fill in the line of best fit as a curved line, because that's what actually fits it better. Best way to do this is to kind of do it by eye and maybe practice sweeping a little bit. Make sure you've got the right angle with your hand. Let's go. Oh yeah, look at that. That's pretty nice. Nicely curved. There's no squiggles along it, and I'm not putting down lots of lines like that. Just be confident, put one nice smooth line in, maybe make sure it actually gets to that last one. There we go. I can always rub it out with rubber if I'm not happy with what it is, but I'm quite happy with how clean and smooth that looks. It's going through all the points nice and close. I'm tempted to put that through 0, but good scientific practice tells us not to try and make up information that we don't already have. So I'm going to avoid that temptation, and I recommend that you avoid that temptation too. So only put your line of best fit in between where your data exists. Question 17b. Part 2. Describe the relationship between potential difference and current. Use data from the graph to support your answer. This is worth 2 marks, so we want to think of 2 good things to say. First of all, we can say that as our potential difference increases, the current does, and then something about that curve. But let's start from the first point. Point number 1, as potential difference increases, current also increases. Let's use some data to back that up. So 1 volt gives 1 amp current, then pick another point. 4.0 volts gives 3.2 amps. So our first point, we've backed it up with some data. Second point, it's not a straight line best to fit, so it's not proportional or anything like that. Best way to explain something like that would be to say something like the current increases at a decreasing rate. And although the word rate is usually referring to things to do with time, let's back that up with some data so you know exactly what we mean. So 1 volt increasing to 2 volts gives an increase of current by, how much has it increased? 0.9 amps. Okay, so what I'm saying is that increasing the voltage by 1 increases our current by 0.9 when I'm at this section of the graph. And then let's pick something else later on, so 4 to 5. So 4 volts to 5 volts gives an increase of current. How much has that gone up by? It goes from 3.2 to 3.2345. 0.3 amps. So a 1 volt increase gives us 0.9 amps increase down here on the graph. Up here on the graph, a 1 volt increase again gives us a much smaller increase in current. So we're justifying our second point there. Question 17b, part 3. Explain how you could use a circuit in figure 17.1 to investigate the resistance of a fixed resistor instead of a lamp. So this was our figure again, and as I mentioned before, to get the resistance of our lamp we needed its potential difference, well, the potential difference across it and the current going through it. So if we wanted to do the same thing but for, what was it, a fixed resistor, we would just swap out this for a resistor and measure the potential difference across the resistor and then the current through the resistor. So let's write something along those lines. Change lamp for fixed resistor, then take current readings for multiple potential differences across the resistor. So that's what we'd change, and this is what we'd do to get all the information we need, because we need a big set of data for voltages and a big set of data for current, allowing us to make a graph current against V to show us how our resistance is behaving. Question 17b, part 4. Explain how and why the graph in figure 17.2 would look different for a fixed resistor at a constant temperature. Just as a reminder, this is what our graph looked like for our lamp, nice and curved, looking like our typical filament lamp graph just here. So for our fixed resistor at a constant temperature, this is quite an interesting piece of information because changing the temperature of a conductor can change its resistance. So a fixed resistor, which isn't changing temperature, is going to behave very well. We're going to get a graph that looks like the typical voltage current characteristics for a fixed resistor, which is a straight line through the origin. So for our 2 marks here, what we need to do is, well, explain how and why. So how will it look different? Well, the graph will be a straight line through the origin. We can go one step further and say that the current will be proportional to voltage. And why is this the case? Well, the resistance is constant. So R equals V over I. Don't really need to include this bit of information here, I'm just showing off a bit, but the graph will be a straight line through the origin because our resistance is not changing. The relationship between I and V is the same no matter what's going on because our resistor is fixed and it's kept at the same temperature.